for exercise 1.4. This video is very essential for the sums that are given under exercise 1.4, which discusses on the various operations on real numbers. Between rational and irrational numbers, if we do some operations like addition, subtraction, multiplication, division, what could be the resultant be? Let's look into each one of these separate cases. Between any rational numbers, it follows the commutative property, associative property, as well as the distributive property. If you look into the closure property between rational numbers, the plus, minus, multiply and divide, they are all closed, meaning the resultant will always be a rational number. If you look into the irrational numbers, between any two irrational numbers, it follows the commutative property. Between any three irrational numbers, it follows the associative as well as the distributive properties as I have mentioned here. If we look into the closure property, that is between the irrational numbers, if you add any two irrational numbers, it need not be an irrational. As well as if you look into the minus, like if you subtract one irrational number from another, it might yield a rational number also. Same with the case of multiplication and division, with the proof looking into the examples which are discussed here. In the previous slide, we were looking into the operations between any two or any three rational numbers and between any two or any three irrational numbers. Now, let's look into the property of how these numbers behave if the operation is between a rational number and an irrational number. If you add or subtract any two, one being a rational and the other being an irrational number, the resultant is always an irrational number. You can look into the examples given. These are with reference to the textbook example 11. If we discuss one particular example, root 2 plus 21, root 2 being an irrational number, 21 being a rational number, as you can understand very well, it will result in an irrational number, say 22.41242, which is an irrational number. The next set of examples are between a non-zero rational and an irrational number with the operand, with the operator being multiplication or division, in which case it will result in an irrational number only, meaning they are non-terminating and recurring decimals. These are with reference to the textbook example 11, where they have discussed dividing a rational number by an irrational number 7 root 5 yielding an irrational number, and multiplying a rational with an irrational 7 with root 5 yielding an irrational number. The third case is the irrational number between any two irrational numbers. How does the operators plus, minus, multiply and divide behave? The resultant could either be a rational or an irrational number. Let's look into the three specific examples given in the textbook. These are with reference to the textbook examples 12, 13 and 14, wherein the operator of addition between and two irrational numbers yielding an irrational number, multiplying two irrationals giving rise to a rational number, and dividing two irrational numbers leading an irrational number. Let's understand some identities that are followed in the square root of real numbers. These are very simple, but they are very essential in case of square root numbers. Many of these identities follow closely with the algebraic identities. The first one is root of AB, which is root A into root B. The second one is root A divided by B, which is root A divided by root B. Third one is root of A plus root B, the whole multiplied with root of A minus root B, yielding A minus B. This follows a simple algebraic identity, x plus y into x minus y, giving rise to x squared minus y squared. Same with the property number 4. You can understand very well, where A, if you look carefully, is not a root variable, but B is square root B. So the answer will be A squared minus B. The fifth one is root a plus root b and root c plus root d, giving rise to root of ac plus root ad plus root bc plus root bd. This follows the distributive law of multiplication over addition of real numbers. Now the last one, it follows the algebraic identity x plus y the whole squared is equal to x plus y times x plus y, which is x squared plus y squared plus 2xy. This algebraic identity is being followed for root a plus root b the whole squared. This is the long division method to find the square root of different numerals rounded to 3 decimal places. Why do we need to know about this? In the exercise, it is discussed as operations of root 2, root 5 and so on. Say all of a sudden for the exam point of view, if you are given a different number for which you need to find the square root, you will use this kind of a long division method. So it is mandatory that we understand how the long division method works. Let's look into some specific examples of root 2. How do we write root 2? 2.0, I am taking 6 decimal places. The decimal places in sets of 2. Why? We are going to find the square root. So, you should consider set of 2 zeros in the decimal places. If you consider the whole number, that is a digit before the decimal point. There is only one digit. So, the perfect square which is less than or equal to 2 is 1. So I put 1 and the remainder I get is 1. In normal division, you will bring down only the next one digit which is coming after. But for finding the square root using the long division, you have to bring down the digits in sets of 2. So I will bring down the first 2 zeros, the green zeros which I have color marked so that you can better understand. Now, how do we get this number 24, which you need to divide the 100 with? This 24 is nothing but, I will consider the quotient 1 in this case. This 1, I will multiply it by 2, where I'll get the number 2. But how do I get 24? I will choose the number in the units place. So, and the same number will follow in the quotient, so that the product of 24 with 4 will give rise to a number which is less than this 100. So I am choosing 24 multiplied by 4, which gives 96. The remainder now becomes 4, bringing down 2 zeros. Why? It's a long division method to find the square. So I will bring down the numbers in sets of 2. This becomes 400. Till now, what was the quotient? It is 14. This 14, you multiply it by 2 to get 28. Right. So, but the number I have written here is 281. How do I choose 1? I will choose 1 because this 281 multiplied by 1 gives rise to a number which will give a remainder not more than 400. So, 281 multiplied by 1 gives rise to 281. If you subtract 281 from 400, you get 119, which is less than 281. So I'll bring down the next two sets of zeros. Similarly, now I have 141 in the quotient multiplied by 2 to get 284. You choose the number 4, so that if you multiply 2824 by the number 4, you get a number where the remainder is not more than 2824. So the answer to this root 2 is 1.414. This is the square root of value of this is the square root value of 2. The same method can be implemented to find the square root of 5 and 9. 9 being a perfect square, you don't have any decimal expansions here. It's just 3 times 3, which is equal to 9. Root 17. I should take sets of 2 before the decimal number. So I consider 17. The immediate perfect square which is less than 17 is 16. So 4 times 4 is 16. The remainder becomes 1. Now I bring down the green shaded zeros. I will bring down in sets of 2. Why? It's a long division method to find the square root of a number. Considering 0, now what do we have as a divisor? The quotient now is 4. I'll multiply it by 2 to get 8. I choose 1, so that 81 multiplied by 1 gives rise to 81, so that I get the remainder as 19, which is not more than 81. I'll bring down the next two set of zeros. Now, the quotient I have is 41. Multiplying by 2 gives rise to 82. I choose 2, so that 822 multiplied by 2 gives rise to 1644. The remainder in this case is 256. I'll bring down the next two zeros. Now, the quotient I have is 412 multiplied by 2 is 824. I choose 3, so that 8243 multiplied by 3 gives 24729. The remainder is 871. So, the value of root 2 is 4.123. The next sum is square root of 256. We know that 256 gives rise is a perfect square. So, 16 16s are 256. As you can very well understand looking at how the working goes. Let's look into the next example, root of 1124. How do we do this? As I told you, the whole numbers also we should consider it in sets of 2 right from the units place. So, if there are 3 numbers in the units place, you will consider the units and tens place as one block and the remaining hundreds place one digit as another block. Now, we have 4 digits in the whole numbers. So, 24 as the first block, 11 as the second block. Right. So, we consider 11. The perfect square which is less than 11 is 9. 3 times 3 gives rise to 9. The remainder is 2. Now you bring down 24. Why? We are looking into the long division method to find the to find the square root. So I'll bring down 24. Now the quotient I have is 3. 3 times 2 is 6. I choose 3. So that 63 multiplied by 3 gives rise to 189. The remainder is 35. I will bring down the first set of zeros, which makes us 3500. The quotient I have now is 33. 33 multiplied by 2 is 66. I choose 5, so that 66 times 5 is 3325. Find out the remainder. What quotient do I have? 335 multiplied by 2 gives rise to 670. I choose 2, so that 6702 multiplied by 2 gives rise to 13404. Find out the remainder. What quotient do I have now? 3352 multiplied by 2 gives 6704. I choose 6, so that 67046 multiplied by 6 gives 402276, and then I get a remainder. Now the answer to this question is 33.526, which is the square root of 1124 rounded to 3 decimal places. Let's see how to find the square root of numbers geometrically. We do the following assumptions. AB is equal to x. We need to find the value of square root of x. So for this we assume AB to be equal to x. BC is equal to 1. So the entire length AC will become equal to x plus 1. What do we infer from this diagram? OA is nothing but the radius of the semicircle, which is equal to OC and which is equal to OD as well, because it is the radius throughout. How do we find the value of OC or OA or OD? It is nothing but the diameter by 2, which is AC by 2, which is equal to x plus 1 by 2. Now, how do we find the value of OB? OB is nothing but AB minus OA. We know the value of AB to be equal to x and OA as the radius in the previous step, which is nothing but x plus 1 by 2. Evaluating x minus x plus 1 by 2 is equal to x minus 1 by 2. According to Pythagoras theorem, OD squared is equal to OB squared plus BD squared. We need to find BD. So, BD squared is nothing but OD squared minus OB squared. Representing the values of OD and OB, we get the value of BD squared to be equal to x, and hence BD is equal to root x.